We need a higher theory, and that's where string theory comes in. String theory takes you before the Big Bang, before Genesis itself.
Over the last 30 years, there has been one theoretical framework that has been suggested that could unite the concepts of gravity and quantum mechanics. This framework is known as string theory. But while this attempts to address questions of the fundamental problems in the physics of the universe, so far it has failed to live up to its promise, despite being one of the most useful sets of tools in science. Keep watching until the end of this video to understand more about string theory. The answers are truly mind-boggling. The string theory is considered by many as a dream concept, which could possibly provide a more coherent understanding of how the universe works. But many scientists also declare it to be an existing nightmare, as the theory can't seem to explain so many other concepts. This is why string theory is perhaps the most controversial big idea in all of science today. Many physicists consider string theory to be the current best hope for combining quantum physics and gravity into a unified theory of everything. Yet, a contrary opinion is that the concept is practically pseudoscience, as it seems to be nearly impossible to test through experiments. This is why an increasing number of physicists are becoming skeptical that string theory can unite the fundamental forces of nature. When it comes to scientific fields, physics is regarded as the most potent and precise, and for decades, string theory has been the leading candidate for a unified theory of physics, which now, many seem to argue, is so flawed that it is not even wrong. String theory came into the scene about 30 years ago, and since that time, the interested public has been fascinated with it. This mathematical construct has been popularized through numerous informative platforms, through papers and documentaries, that have pushed for a definitive understanding of string theory in the efforts of uniting physics into one grand theory. Added with the fact that the theory also espouses strange implications such as extra dimensions and possibly even a multiverse, the concept's popularity has massively soared. But while the idea may be popular, with more scientific papers arising from it than any other concept, string theory hasn't really produced any testable predication in all this time, not even one, leading many to decry that the theory hasn't risen to the standards of science. What is string theory? String theory is a hypothetical theoretical framework that attempts to be the theory of everything, able to explain the fundamental microscopic aspects of all reality, from the forces of nature to the building blocks of matter. The starting point for string theory is the concept that point-like particles of particle physics can be modeled as one-dimensional objects called strings. The theory describes how these strings can propagate through space and interact with each other. In any given version of the string theory, there is only one kind of string, which may appear as a small loop or segment of ordinary string, which can vibrate in different ways. A string can look like an ordinary particle, with its mass, charge, and other properties determined by its vibrational state. One of the most interesting concepts of the string theory is its postulation that we live in a universe of 11 dimensions. These includes up, down, left, right, forward, backward, time, and 7 other dimensions that are impossible to observe. The smallest particles of matter that we can actually see aren't small dots or spheres, but are rather tiny strings with vibrational modes. The vibrations would sing out quarks, electrons, gluons, and photons, as well as all the other elements of matter, to produce everything needed to create reality. Mathematically, the theory seemed to provide a simple way of solving problems in fundamental physics, including the notorious mismatch between Einstein's smoothly warped space-time and the inherently queasy bits of stuff that make up everything in it. But while mathematics is about well-defined ideas, there is currently no such mathematical construct as string theory. However, the problems with string theory have nothing to do with mathematics, but rather with the physical idea of the concept that doesn't work out. And now, even the regard of string theory being a scientific theory is being questioned, since it isn't a physical theory that can be experimented on to provide meaningful findings for science. Despite the elegance of the math behind the string theory, the theory came with unsettling implications. The strings were too small to be probed by experiment and lived in as many as 11 dimensions of space. These dimensions would compactify, or fold in on themselves, into complex origami shapes. No one knew just how the dimensions fold in all together, so the possibilities for it seemed to be endless. But surely some configuration would turn out to be just what was needed to produce known forces and particles already understood by science. How does string theory affect theories of physics? The development of string theory lives on in reputation due to its mathematical beauty, but this concept has been built on numerous prior concepts. Late in the 17th century, Sir Isaac Newton built the first comprehensive mathematical models of the universe. Basing from his experiments and the experiments of his peers, he was able to calculate that the pull of the Earth upon the Moon is 3,600 times weaker than the pull of Earth on an object on its surface, thus leading us to his theory of gravity. His work and findings would later dominate physics for roughly 200 years. By the 1900s, however, more experiments began to find issues with Newton's theory. Over the next few decades of the 20th century, scientists would espouse revolutionary branches of physics to explain those which Newton's theory could not, from Einstein's theory of relativity to the concept of quantum mechanics. Scientists would begin to invent one theory after another, if only to explain the inconceivable, to understand the mysteries of the universe. For the next 50 years or so, theoretical physics would continue to become drastically stranger. New models were developed and accepted using semiconductors to superconductors to provide actual experimental results that were better than previous theories presented. Up until the 1960s, physicists had discovered what they thought to be the fundamental constituents of matter, which are protons, neutrons, and electrons. Scientists of the time had also recently accomplished the feat of unifying quantum mechanics and special relativity with what they called quantum electrodynamics, which was a quantum description of the electromagnetic force. At the time, particle accelerators were just entering their heyday. After the discovery of the antiproton in the 1950s, larger and more energetic particle accelerators began to be constructed, leading to the discovery of an even more enormous suite of new particles, such as baryons, antibaryons, and mesons, that arose from colliding charged particles into another charged particle. The discovery of these even more subset particles, as well as an apparently new force of nature that was governing it all, the strong force, would entice physicists to try new ideas using more mathematical tools. This was when scientists re-encountered an interesting set of ideas first proposed by one of the founders of quantum mechanics, Werner Heisenberg, back in the 1930s. His idea was to skip all the necessary work and develop a machine called the scattering matrix, or S-matrix, that immediately jumps from the initial state to the final state, which would then provide what is intended for measurement. This approach would be revived in the 1960s, as theorists extended and developed the S-matrix concepts using mathematical functions that were especially powerful to provide a traditional interpretation in terms of time and space, while also following the evolution of particles. This was how scientists found something surprising, according to the mathematics, that in order to describe the strong nuclear force that binds everything together, it had to be carried by tiny, vibrating strings. These strings appeared to be the basic building block of the strong force, with quantum mechanical vibrations determining their properties in the microscopic world. In essence, the vibrations of the strings would make them look and act like tiny particles. However, this string theory was difficult to work with, making predictions nearly impossible. It also required the existence of particles that travel faster than the speed of light, called tachyons, in order for data to be collected. This theory also postulates that there are 26 dimensions in order for it all to make sense mathematically, which is quite a jump from our known universe's 4 dimensions. As of present day, Einstein's general relativity is still our leading theory of gravity, which has passed every experimental and observational test, including gravitational lensing to relativistic frame dragging. Other fundamental forces of the universe, such as electromagnetism and the strong and weak nuclear forces, which are described under quantum field theories, still remain unresolved, indicating that there is more to the universe than we currently understand. In 2013, theoretical physicists attended a conference which represented an even split at the idea that string theory can unite physics. While many still hold on to string theory as possibly being able to unite physics into one grand theory, many still consider it a failed theory because it hasn't made any useful predictions about the universe. As further studies continue, we remain to wonder about the mysteries of the universe and the fundamental forces that keep it together. What do you think about the string theory? Let us know in the comments below. Thanks for tuning in to StarBurst. We hope you've enjoyed this video and learned something new about our incredible universe. Don't forget to subscribe to our channel for more exciting content, and hit the notification bell so you never miss an episode.